Okay, I thought this time we'd do a little bit model validation, try and see how close the predictions RC crew chief makes in the acceleration simulation to what we actually measured on the chassis dyno. So here's what we're going to do, and try and do this as quickly as possible. So first thing is we got to extract some chassis dyno results. Then we're going to create a motor and battery model from the motor dyno testing we did at the same time. And then we're going to run the acceleration simulation, and we'll adjust the variables to match the match the chassis dyno testing. So first step is to extract some chassis dyno results. So what I did here is I just took one of the runs on the chassis dyno and processed it through RC crew chief, and then in the graphing section just went through and picked off points at various time intervals. This is the RPM versus time, this is the current versus time, and this is the battery voltage versus time. So it just went at 0.1 seconds, half a second, 1 second, so on up, and extracted out the RPM, the current, and the voltage. So did that at all the points and just summarize that in a graph. As I mentioned in the previous episode or two, RC crew chief doesn't import the speed, so we have to do a correction there. Essentially, it's just the kph, kilometers per hour, is just the RPM measured, KRPM measured, times 11.25. So that's your first row here is your kph, then your voltage, and then your current. So next up, we need to create some models. So in RC crew chief again, what I do, manager, is load a file that we recorded using the same motor, same ESC. So I'm just going to open one of these guys up here, and I'm going to switch it to a different file format, and there's the RPM versus time for that run. So if we do a dyno analysis on that, and then what we're going to do is we're going to create a motor model. So we're also going to create a battery model, and the battery model is basically the numbers that are sitting right here. What the simulation does is take the voltage versus current data and graph it one versus the other, and then fits a linear line through it. So you can get the no load voltage and the internal resistance of the battery. It's actually the internal resistance of everything you've got connected up there, to give you a simulated voltage source. So this will become our battery model, which I'll show you in a minute. I'm not going to go in great detail here. I'm actually going to take a bit of a pause, and I will create the model, and then I'll show you how it compares. Okay, so I've adjusted all the parameters here to get as close a match as I can to the actual test data. So the red line, in this case, here's the power curve. The blue line is the dyno results. So there's the match I got for the power. This is the current through the stator, the efficiency, and the torque. So you can see the curves match pretty close. Not a bad result at all. So now what we're going to do is we're going to create a motor model, or sorry, a battery model, which I've already done here, based on that test battery information that I showed you. So the actual results, we've got a voltage per cell of 4.08 volts. Battery was not 100% charged. I always go to a little less than 100%. charge, just because it takes that little bit of peak out of it and you get more into the flatter region of the discharge curve, and the internal resistance, and that's essentially it. So now if we go to the acceleration tab, what I'm going to do is I'm just going to adjust the parameters for car 2, so ignore whatever we see up here for car 1. So first thing we want to do is change the motor. So we're going to change the motor to the model that we just created, which is this guy. We're going to change the battery to the battery model that we created. And we'll change this to a Pro ESC, but it doesn't really make a whole bunch of difference in the simulation. So next thing is we need to adjust our gearing, and we're at 3.71 to 1 is the gear ratio. And last but not least, we need to change some of the other simulation parameters. So the first thing is the vehicle mass. You can convert the inertia of the drums to an equivalent mass. So it's basically what the inertia of all the rotating components in the dyno divided by the radius of the drum squared. So with the setup I had, that worked out to be about 1,765 grams. Aero, we don't have any aero because the car is not actually moving, so we just zero all that out. And that leaves us with these two parameters that we can use to tweak the results to see what kind of a match we can get, because we've got different rolling resistance and different mechanical efficiency, because we've got all the belts and bearings and stuff for the dyno that we need to take into consideration. So I'm just going to apply that without changing anything. So now you can see that our performance has dropped off quite a bit from what the model with, trying to simulate real world. The other thing I want to do is I want to increase the runtime up to 4 seconds, because that's what we were doing. 4 seconds. Okay, so now what we need to do is adjust our rolling resistance and mechanical efficiency to see what kind of a match we can get. I went through a number of iterations on this, and what I ended up coming up with was 74% and 0.15. Now the increase in the rolling resistance coefficient makes a fair amount of sense, because the car is strapped down hard to the dyno, so the tire makes a much bigger footprint on the roller than it would on carpet around the ground when you're running it. Actually, I think it's 0.16 if I remember right. And this rolling resistance coefficient, basically it's a friction factor that's going to apply regardless of RPM. It's just a constant loss in torque. So the mechanical efficiency, now that applies directly to the torque. So you take 74% of whatever torque is developed by the motor, and that's how much gets applied to the wheels. So if we apply that, close this out. And then what we can do is we just go as we did with the testing data, and we just click on the various different points, and we get speed for Model 2, and we just played around with those numbers until we got a good match. And you can see here, that's the graph. So this is a summary. So this is the chassis dyno that we showed before, and this is what we ended up with RC Crew Chief. So the green column compares to green, orange to orange, blue to blue. So you can see our kph is very close. We're within a few tenths of a kph all the way through. Our current and voltage, however, are not as good, but they're still in the same sort of trend. One of the problems here is that they're using two different voltage and current measuring sensors, so there's some differences there, which could attribute the discrepancies that you see here. But all in all, not bad. At 4 seconds, the dyno was doing 52.3, and the simulation said 52.7. So I'm sure I could play around with the numbers a bit more and get it even better, but just wanted to get a little insight into how valid the acceleration model in RC Crew Chief is. And that's it.